Just thought I'd make a tutorial showing how you can use HLSL directly in Monogame. You can probably do the same thing with GLSL, except I don't know exactly how to do that yet because I haven't tried to make it work yet. We'll start a Windows project. I'll name it HLSL game, I guess. Just gonna tidy this up a bit first. Alright, for graphics, for the dimensions, the resolution you want, you probably know all this stuff. Depth format I'm going to set to none, because we're not going to need it for this effect. I've kind of made a habit of setting graphics profile to high def. We're going to have an init shaders method in here. I moved SpriteBatch from load content up into initialize just because it seems more appropriate to me. We're going to load our shaders in here, and that's why I'm going to call this init shader vars here instead of in the init, because they need to be loaded before we can set their parameters. We're probably going to call a dispose in unload content for our shader manager. So the first thing we're going to do is go over the name of your project over here in Solution Explorer, right click on it, manage NuGet packages, click on browse. So here we're going to type in SharpDX, and I think we're going to need this one. We'll click install, click OK. The DXGI, I'm pretty sure we need that. D3D compiler, click install. Okay, so yeah, SharpDX, DXGI, we'll need these two for sure. The D3D compiler we'll need for the HLSL stuff. And mathematics, we'll install that one. The 2D, install, okay, and the 3D11, install. And out of the SharpDX stuff, I think that's all I might be using in this project. So everything else will be Monogame, which is actually using SharpDX. So we got this one, this one, this one, this one, and this one, and this one. So double click on game one, go back there. And first of all, let's create an effect file, or you can grab an effect file that you already have made for HLSL. In fact, what we'll do is we'll go new, file, shader file, and click open, and we'll start building a shader file. I'm just going to copy from an old HLSL file that I'm using as an example and paste it in here, and then I'll just show you what I did. So I renamed that HLSL underwater pixel shader.HLSL. It could be used for underwater or just water surfaces. I just got this definition here, sample text. Anytime you see sample text, it's going to substitute it with this sampler here. So for parameters, I got texture. This sample type thing here is just used with texture sampling here, sample type. I got this constant buffer, and we use that for passing parameters. So I'm just calling it water buffer, and we're going to pass in a timer value, water top value, which is where the top of the water is, whether or not to just distort it, and a float value for padding. And the reason for that is we want to use a 16-byte alignment structure, and that's for cache optimization purposes. So you want your parameters to fit in groups of 16 bytes basically. So you got 4 here because the float is 4, 4 here. Bool is technically an int, so that's another 4, and this is another 4. If I just had these, I don't think it would work right. It might not work at all, if I remember correctly. I'm usually using effects files and doing stuff directly in Monogame. And just to keep things tidy, I made this structure to put the input parameters in. So based on the Vertex shader that's standard to SpriteBatch, I'm using position first, then color, and then the texture coordinate with this SV position, color 0, text chord 0, so as to make sure that it's compatible with the Vertex shader that SpriteBatch uses. And we can create our own Vertex shader HLSL, so you'd have like an underwater VS and an underwater PS, two separate HLSL files that you'd convert and make into shader-byte-code and then use in your game. In this case, we just want to modify the pixel shader that SpriteBatch is using by default and introduce our own made in HLSL. So for the shader itself, we get those input parameters here, this, and output style is SV target. Keep in mind, I made this shader specifically for an 800 by 600 resolution, and this is just a hard coding, assuming that the space for the water is 128 in height. So anywhere where there'd be water for this particular shader, this is static. So normally you'd want to pass in parameters for this sort of stuff. And as I commented here, this is the same as 1 divided by 600. So it's 1/28 out of 600 in height, and that's just a constant. So this is just accepting the texture coordinate from here, so we can just refer to it as UV instead of having to say input.uv all the time. This is calculating where the bottom of the water is, so it'd be the top of the water that we gave it up here in the constant buffer, which is where we pass our parameters, and we're adding in the texture height, which we made static here. So it would be some kind of fraction of 0 to 1. I guess you could think of it as a percentage. And I'm going color equals sample text. All that's really doing is replacing this with this. So it's doing a texture sampling using this sampler type and the texture that we pass in. So after we've got the color sampled into here, then I check to see if the Y value is under the water level. And I add this cos timer value so that the water level kind of bobs up and down a bit. And so what it does is at the X coordinate for the water and the Y coordinate for the water, it's adding this waving effect. And that's what this sine timer thing is doing. I add in this UV times 10 thing here to create some variety based on where it is sampling from. So it's not sampling the same wobbling distortion at every single pixel, but it's adding extra rotation, I guess you could say, to the sine function and cos function based on where it is. And then here we're just scaling it so that the amount is some fraction between 0 and 100. And in this case, it's going to be like 0.4%, so 0.004 to get it between 0 and 1. So it's only moving it a tiny little bit. So now we're going to get the color at this new UV coordinate, because this samples wherever this UV is. And if we're not just distorting it, and I think in our case we are just distorting it because we're not doing anything underwater, we check to see if the coordinate isn't past the bottom of the water, because we don't want to go that far down because we might have a higher bottom for the water. We calculate the percentage down into the water that it is based on the current coordinate where the water top is, so the distance between those two positions, and we're dividing that up by the texture height to get the percentage down. And then the alpha value is modified from 1 to percent down. So if percent down is 100%, then alpha is going to be 0 and it's going to be totally see-through. So the further down into the water it goes, the more see-through it gets. So this part of the shader is actually for the underwater, the actual underwater part, which we're actually not going to use in this demonstration. But just for those who are interested in how this works, I'm just kind of showing what it's doing. So this part here is a little bit redundant. I could actually just copied it from color because I already have that. And then what we're doing here is really confusing to look at. This is the distance down, which is some percentage between 0 to 1. And we're saying 1 minus that amount. We're subtracting this 0.5 to get this to scale between negative 0.5 and positive 0.5. So the horizontal range is going to be stretched out based on this distance down into the water. So the bigger this distance is, the wider this horizontal offset's going to be. Then we have to add in the 0.5 again to get it relative to 0. So it's instead of going negative 0.5 to positive 0.5, it's going to go 0 to 1 again, timesing it by 2 to increase the effect. And then, so that's creating a scale for this horizontal coordinate between negative 0.5 and positive 0.5, and it's widening it, making it wider based on that distance. So that stretches out the horizontal sampling position based on how far into the water it is. As far as the vertical sampling position goes, the reason why we're going water top minus UV minus water top, this is the distance into the water, timesing it by 2, so it's sampling every second position, but by doing that you're actually squashing the image. And going water top minus that distance, you're basically just flipping the sampling position upside down, so you're creating a reflection. And that's also why we did that here. This is so that we're basing it on the reflection amount, or the reflection position. So we multiply the alpha by the pixel sampled at that mirrored location, and so we got that sort of semi-transparent reflected color right here. And we're adding in the color sampled behind it normally and multiplying by percent down, which is going to act as the alpha. So keep in mind that the alpha is collecting the other half of the percentage. This alpha plus this percent down adds up to 100% of your opacity of 1.0. Alpha is the difference between 1 and %down, and %down is the collection of the other portion of the color, which is sampled here. And now that I think about it, I don't know why this line is in here. Color 1 is equal to sample text. I think I was doing something with adding an extra color amount before, and I still have this in here. I'm not sure why, but we can probably do without that line. So when we get to the end, we just multiply the input color, which we might have used in SpriteBatch or some other batcher, which could supply its own colorization amount, and we'll multiply that by the color that we calculated here. We're probably going to be using color.white, so it's just going to give it a 100% value. If we used like blue, for example, it would make it a blue or sort of a bluish tint. So this one would probably be in your SpriteBatch draw, whatever color value you wanted to use. I'm just going to go ahead and quickly make a C++ project where I can just compile the shaders in there and then bring them over. So I'm going to go File, New Project, making sure we saved our other one, and I'm going to go to Visual C++ here, and it's going to do Windows Console project, or no, I'm going to do empty project, and I'll call this HLSL compile. This might not be necessary, there might be another easier way to do this, I don't know. This is just how I've been doing it. We'll right click on the source files and we'll add new item, C++ file, and I'm going to call it WinMain. And I just kind of copy and paste in some standard code that I always use for this, for when I first start a Windows project. Okay, so I just got this windows.h added up here. This is a standard call to your entry point for your program if you're doing a Windows project. This is just for setting up the Windows class and registering it, and this is for creating the window itself. I don't even know if you need this stuff, but I just put it in here anyway. So we're going to go over here to source files. We're going to add in that underwater HLSL that we made. So I'm going to add existing item. And I got two other HLSLs here too. I'll just grab those two. We'll add them all at once. These are just empty pixel shader, vertex shader types. So for example, if you wanted a vertex shader, you'd pass in your parameters for your matrix transform with this. So this would be your constant buffer. This is 16 byte aligned already, so you don't have to worry about that. And we're doing it like the SpriteBatcher, so using kind of a standard format for these, so everything's compatible. I'm using the worldview projection matrix, multiplying it by the position to get where it is on the screen. And this actually could be used just like the vertex shader that's sort of standard for your sprites too. So you can use it with the SpriteBatch, you can use it with your 3D geometry, and you can make versions of this that are a little more advanced, where you're adding normals and normal lighting and all that stuff. This is just a basic pixel shader HLSL. So you got your texture here, texture sampler here. We'd probably need to change this to match whatever's coming out of the vertex shader. Actually, I think with HLSL is a little more forgiving. You can actually just take certain parameters if you want. And output is SV target 0, standard sampling of color at a position on a texture and multiplying it by the colorization that we sent in. So I'm going to right click on underwater HLSL and I'm going to click on compile, and that's how we're going to make it into a shader object that we can use in our project. So it's shader-byte-code essentially. So click on compile. And let's see what went wrong here. Invalid semantic. Vertex shader 2 it says here. We're not trying to compile a vertex shader, so let's go to properties of underwater pixel shader and not forget to set those. I don't know why I at some point changed this. Anyway, I just want to use this. Let's copy the name of the shader here. Right click on the shader and click on properties. Click on all options, and where it says entry point name, change main, and we'll paste the name of the pixel shader. So that's what it's going to look for. This would be your output directory, output file name option. You could change that if you wanted. You could make it go directly into the project that you're going to use your CSOs in. That's a compiled shader object, which is shader-byte-code. And we're going to use a pixel shader model 50. Shader type is pixel shader. The interesting thing about using HLSL is we also have the option of using geometry shaders, and we have access to all of these. So I think currently we don't have access to a geometry shader normally in Monogame, but if you're using this technique, then you can use a geometry shader. So we're going to use a pixel shader, apply, and OK. Now we'll try to compile it. and it compiled the CSO. What I usually do is I keep a couple of these folders open, one which will be set to where my CSOs are deposited and one to where I want to copy them to. So I can just drag from one window into the other one, and it'll always copy my updated CSOs in there as I need them. So if we're using a debug version of the project, you can click on the debug and you'll find your CSO in there. And I'm just going to open up another window so that I can drag them from one to the other. So in our HLSL game, just a side note, you'll notice these packages here. If you ever need to remember what it was that we were adding to the SharpDX based projects, those are all in your packages folder. Okay, so we're going to go into bin for binary Windows and the debug folder for now. We'll probably want to put a version into the release version when everything's ready for release. So we'll drag from this HLSL compile, actually no, let's copy and then go over here and paste. So anytime we need to update these, as long as these two are kind of open in the background, we can just copy and paste to update them as we need to. So I'm going to minimize those two windows. Also, I'd have two versions of Microsoft Visual Studio running. One so that I can do a compile update on the HLSL, and the other one for the project that's using the shader object that we created. Back in HLSL game, let's right click on the project and we'll add a class. And I'm going to call mine HLSL effect. For now, we're going to set up our constant buffers just directly in here because we're only going to use one HLSL effect. So I just pasted this in here from a previous trial. What we got here, oops, let's go like this. So the structure layout has to be aligned to 16 bytes. And then we got this public constant buffer. And this one's specifically for the pixel shader that we created, that water one. So the first parameter at field offset 0 is timer. Second parameter, and the float is 4, so the next offset is going to be 4 because we've used up the first 4. And it's going to be the water top. We go another 4 down to get to 8, and then an integer. So the boolean's actually an integer, and that's the same as the float. It's 4 also. And this is just to determine whether we're only using distortion, which in our example here I think we will just use the surface distortion rather than the underwater stuff. And we'll need to add in padding so that this is 16 byte aligned, and so it's going to be cache optimal, and I think it needs that. So that is how you set up your constant buffers, and there's more on Microsoft websites on how to set up constant buffers for HLSL for more complex shaders. So go into the HLSL effect here, so we'll just set this as public, and let's make this disposable too. We'll go using system, and it'll want us to implement this. It's going to declare a boolean here, disposed false. Okay, so this is your standard dispose type setup. Normally if we call dispose from within game 1, for example, it's not exiting the program, so we do the suppress finalize, and we call dispose here true disposing. If it's already done, it returns like you already did it for some reason. So here we would dispose of any of the managed stuff that we want to dispose of. And here we are disposing of the unmanaged stuff that we want it to dispose of when it exits the program. And we set dispose to be true because we already disposed of it. And this is the destructor which just calls the dispose method. So when the program exits, it's just going to automatically call dispose, and we don't want to do the suppress finalize because we're exiting the program, so it's just going to dispose of everything. Hopefully that's clear as mud. That's not really relevant to this tutorial, but there it is anyway. So copying that from here, I'm going to want my variables in here. I'm just going to call them bars. For convenience, we'll go up to using, and we'll say d3d is equal to SharpDX. Should be SharpDX.direct3d11. So that's the one we're going to use. Okay, so down here, I can say d3d dot, and we want a constant buffer. So C buffer, something like that. Constant buffer. What the hell? What's it called? Oh yeah, I think this is just a buffer. And then I'll say constant buffer PS. So that's the pixel shader's constant buffer. That's what we're using to pass our parameters. Okay, and also need the device in here. This is pretty much standard direct 3D. You get your device and your device context, which I'll call DVC, because I always call it DVC in dev. You might want to just call this device and call this device context, but let's keep them short. Private. Oh geez, that's almost as bad. Alright, and we want a pixel shader. So it'll be a custom pixel shader. Now we're going to need access to some things. I'm going to use SharpDX Direct3D11. That should take care of that. Yeah, it shows up here now. So we'll generate a constructor, and that's not quite what I wanted to do. I'm going to call it a constructor. And so first thing, we're going to need access to this device. So let's pass in device, and I'm just going to call it device. And we'll need file name for the effect we want to load. Shader-byte-code file name. So if the file doesn't exist, file dot, it doesn't like that yet. Let's go like this, system.io, there we go. Exists. So if it doesn't exist, we'll write a warning and return. Compiled, pixel, shader, not found. And then we'll show the name of it, file name, and return. So we're going to need access to the device. There's a device that we passed in. And once we got that, we can get the device context from it, immediate context. So using the pixel shader is equal to the shader-byte-code, and using this using thing, it'll dispose of this as soon as we're done using it. And so we're getting this from file name. I don't know why I have this in curly brackets. It should be regular brackets. Let's right click on this. This will need, I think this needs Direct3D compiler. Ah, down here. Using SharpDX D3D compiler. There. So we're going to say that our pixel shader is equal to the new pixel shader using the device and the pixel shader that we just made right here. And then we'll have our actual shader pixel shader rather than just this shader-byte-code. So then this is disposed of right away. So load precompile shader. And if for some reason we end up with null, we'll write a warning and return. As for the constant buffer, we're going to go buffer description, D3D buffer description, and create one. And this is again kind of common Direct3D code for setting this stuff up. Oh, what the hell? This should not be equals here. Equals here, a new description dot device. Oh no, wait, buffer description. Buffer description. Okay, needs a size in bytes. So our description would be size of, we'll use the Marshall size of, type of cbuff. So I'm not even sure how this works, but I know that this is how you do it to get the size of what we made up here. So give it the size. We want it to be resource usage dynamic, bind flags, and it's a constant buffer, and CQ access. And this is all because we want it this way because it's a constant buffer that's being made. And so we won't need any resource option flags. Structure bytes in stride, not worried about that. Like this. So now we can create the constant buffer for the pixel shader. So it's a new D3D buffer using the device and supplying the description it wants. So basically with this stuff here, we've made it the buffer into a dynamic constant buffer where we can update variables on the pixel shader. Now, speaking of updating variables, let's make a public void, make a public void update vars. Or you could just call it update, I suppose. So just to be on the safe side, I check to see if any of this stuff is null, and then return if it is with a warning. So we must have did something wrong in our coding for this to happen. So constant buffer is, I think, is referred to as a mapped sub-resource. I'm going to create a data stream, call it mapped resource, and to do that, I'm going to need to go using SharpDX. So with the device context, we can map that resource, and then we can update our constant buffer, map sub-resource, and we want to update the constant buffer, which has our variables, our parameters we're passing. The map mode is write discard, map flags, none. I'm going to say out mapped resource. So now we have our mapped resource with basically locking for writing. And now we're going to write to that locked space. And we're going to write our vars, which was this thing here, which we made here. technically you're updating your parameter somewhere else. Then you're calling this update vars to tell it to put those into the graphics card. So device context. So we got to unlock everything now so that it can use it. This is just a safe way of updating it so that while something's happening, it's not screwing something else up while we try to modify it. I don't know if I explained that very well, but hopefully that gets the idea across. Okay, so we unmap, and that makes it free to use for the graphics card. And we're going to dispose of this mapped resource thing because we're done using it. And then we're going to set which constant buffer to use. So set constant buffer. We're using slot 1. And the reason we're using slot 1, so this part's important, I forgot to explain this. When we made our constant buffer in our shader, I was using register B1 instead of B0 because B0 is already used up. If we're using SpriteBatch or another batcher, B0 is already used up by the first shader that's in there. So we want to use B1 for the constant buffer for this because B0 is used with the matrix for the worldview projection of the vertices. So B1 for this one, and for any other constant buffers after it would be like B2, B3, and so on. And you have to have a corresponding slot to match too. So right here, and I should put a big note right here, use matching register B1 is equal to slot 1 for constant buffer. So if you're using a bunch of different constant buffers for different effects, you'd probably want your update vars to pass in a slot value like int slot. I'm just going to put slot here, and we'll just do it that way to make sure that we're not using the wrong slot. I guess another way we could do it too, well, that's just getting into making the code more modular. I'll let you figure that out on your own. So since we're only going to use one shader here, I'm just going to take this out, and we'll just use slot 1. But just remember that that's important. So that's all there really is. The HLSL effect is your constant buffer, your constructor, which takes a file name and loads the shader-byte-code here, and then creates a description, and then creates a buffer based on the description so that it knows it's a constant buffer. And then the thing that locks the memory space so that you can put the updated constant variables in, update the parameters basically, and then it unlocks it so that the graphics card can use it again, and it'll make sure we know what slot we're using, so which constant buffer to put them into. Back in game 1, we'll add a test background to apply the effect to. And we'll load that in load content. Background is equal to content load texture 2D, and we'll need to go into content here, double click it, and add the background. So edit, add. I'm going to add an existing, it'll copy it into the directory, and once it's in there, I'll save it, build it, background. First thing I want to do is make sure it loaded it and just try and draw it here. So SpriteBatch begin, SpriteBatch.end, and SpriteBatch draw. Draw the background, 0. No colorizing, we'll just use white for 100% of each color channel. Okay, so this is the background I'm using without the effect added. We're going to add the effect. This is about 128 pixels up and down here, which is where I came up with that number. And this is a 600 vertical resolution, so that's how I came up with that number. Okay, so the first thing we're going to need access to is the device and the device context. So device, I'm just going to say dev. Direct3D11 we're using, and device context DVC. Now you might notice by adding this SharpDX Direct3D11 thing, we get this conflict here. It doesn't know which one you're referring to. So I'm just going to go up here and using texture 2D is equal to texture 2D. It's equal to that one there. So now it knows. Actually, let's make this simpler. Let's just go, I'll just say X and A is equal to graphics. There. So here I could say X and A texture 2D. It's technically monogame, but X and A is shorter. And while we're here, let's add in our effect, HLSL effect. And let's call it water effects, or water pixel shader. That would be more appropriate. So moving into the constructor, or wait, not in the constructor, we'll go to the initialize because we got to give this some time to sort itself out. We'll come to initialize and set this up in here. So here's where we're going to get our device. Say the device is equal to, and we want Monogame's version of the device. So we're going to say we're going to use Monogame's graphics device thing and get the device from that. So we'll use the handle, and that should return the device that we're using. And it will be cast to a SharpDX Direct3D 11 device. And from that we can get the device context. So just go dev.immediate context. Alright, let's go back up to init shader vars. Actually, you know what? I'm going to move them down under init. So it's kind of more sequential. Well, let's go back into our HLSL effect and make sure these are public. This one's public. This one wasn't public before, by the way. So, okay, and let's go down to our dispose. Let's dispose of the constant buffer and the pixel shader. So if our constant buffer pixel shader is not null, we can dispose of it. Oops. And it has a built-in dispose, so we'll use that. I'm not sure if this part's necessary, but I'm just kind of used to doing this sort of thing in C++. Gave me the wrong one here. And we'll do the same thing with the pixel shader. So if it isn't null, for some weird reason, like we haven't disposed of it yet, which we probably haven't, we're going to dispose of it. There. That takes care of the disposal part. And typically you don't have to worry about disposing things. The garbage collector takes care of a lot of that stuff. So for my particular shader, I'm just setting just distort to false by setting the integer to 0. Starting timer 0, padding 0, we're not worried about that. And water top 73%. From the top of the bitmap to create the reflection region. I figured that out from doing the math on what percentage down it is in the background image. And now, because of the ambiguous reference, we've got to go xna dot, and that takes care of that problem. We call the init shader variables, and let us load the effect too. So I'm using a water pixel shader, so whatever yours is called, maybe HLSL effect. Oops, we're not using GLSL. Maybe later we'll figure out how to do that. And underwater pixel shader CSO. And that CSO will need to be in your binary debug folder, or if you're using a release version, it would be in your binary release folder. So that'll load the shader-byte-code. And then unload, I'm going to call water ps.dispose. And so we're going to update our parameters that need to be updated each frame in the update. So for the timer, which controls sort of the rotation in the sine cos, we're just perpetually adding to it. So it's just looping around in the circle forever. And the water pixel shader update vars has to be copied, or has to be called to copy everything into the right part of the graphics card. You could change this too to make the water ripple faster or slower, whatever. Since our background's filling the whole screen, actually, we can just comment out this line if we want. For our begin, I want to make sure it's deferred so that the effect is applied appropriately. It should be by default anyway. If you use immediate, I think you have to do a little bit differently. You have to do it before the draw call. So we're going to go deferred gfx.blend state, and this is just to get rid of the ambiguity, or xna, I think it was, non-pre-multiplied, and sampler state. I want to use linear wrap. In this case, I'm not worried about depth, so I'll say none. And then we can call SpriteBatch draw the background. And oops, we already did that. Why are we doing that again? I don't know. So right before the end, because this is deferred, it's going to draw everything at once off of our sprite sheet or whatever we're using. In this case, it's just a single background. We'll use the device context to set the pixel shader. Water ps.pixel shader. Okay, now if you're not using SpriteBatch, you'd set up all your 3D states here. Actually, you probably want to do 3D stuff before your 2D stuff, because your 2D stuff would usually overlap. So let's say you're doing 3D. If doing 3D, set up 3D states here. So you probably want to set your depth stencil state on the graphics device. So I'm not going to go over the 3D stuff because that'd be part of a different tutorial. You can refer to some of my other 3D tutorials. But yeah, you'd set your vertex buffer, set your default vertex shader and or pixel shader. Could be one or the other or both. And it doesn't matter if it's an effects file or if you're using the HLSL stuff. So you'd set those, And then you'd have your overriding pixel shader here, which we're also doing here with the SpriteBatch in this example. Now, the reason Vertex Buffer and default shader are underlined, obviously, is because we aren't actually doing that in this example, so it doesn't know what I'm talking about. And then your camera transform you'd set here for the 3D version, which is passed into matrix transform. Then you call to set the pixel shader, set the textures. Any textures after 0 you'd want to pass as a parameter, because doing this would not work, for example. So you'd want to pass it as a parameter, and you probably do that in your update if it's changing. If it's not changing, then you don't have to worry about it. You just do it in the init. And then you draw all your triangles. And since we don't have an index list, vertex list, triangle count, these are all underlined. So if you need to take a screenshot of this, or just pause the video and copy it if you need it for whatever, go ahead and do that. I'm just going to delete this though. And actually, no, let's just put comments around all of it. So that's the general idea behind that. Let's see here. Is there anything we forgot? I mean, really, there's not a whole lot to it. Once it's initially set up, it's actually pretty easy. Okay, so let's build this, see if it works. Doesn't seem like we got any errors. It's a good start. And look at that, it works. Put on the first try. Huh. Nice. The underwater part's not in effect right now because we have distortion, underwater distortion turned off. We're not using it for the scene. Let's just hit escape. So yeah, that's all there is to using HLSL in Monogame. And the nice thing about this too is it gives you access to geometry shaders. If that turns out to come in handy for something, for some people.